Why is algebraic simplification important, you might ask? Well, it's a fundamental process in mathematics that helps us reduce and simplify complex expressions. It's like decluttering a room, making it easier for us to navigate and understand what's going on. Algebraic simplification is not just about making math problems easier to solve, though. It's also about honing our logical reasoning skills. When we simplify an algebraic expression, we're essentially breaking down a problem into smaller, more manageable parts. It's a bit like solving a puzzle, finding the right pieces and fitting them together in the most efficient way possible. And it's not just in the realm of mathematics that these skills come in handy. Whether it's planning a project, making a decision, or even organizing our thoughts, the ability to simplify and break down complex problems can be a real game changer. Now that we understand the importance, let's dive into the techniques of algebraic simplification. Starting with Boolean identities, which are the foundation of algebraic simplification. These identities form the backbone of Boolean algebra and are the fundamental laws we use to simplify expressions. Firstly, we've got the identity law. In essence, this law states that any value ORed with 0 or ANDed with 1 will always return the original value. It's like adding 0 or multiplying by 1 in standard algebra. Next, we have the domination law. This law asserts that any value ORed with its negation will always result in 1, and any value ANDed with its negation will always produce 0. The domination law is all about extremes 0 and 1. Lastly, we have the idempotent law. This law succinctly states that any value ORed or ANDed with itself will always be itself. These laws might seem simple or even trivial, but trust me, they are the building blocks of more complex simplifications. With this understanding of Boolean identities, we can move on to the next technique. Next up, we have the commutative law and the associative law. These laws are pillars of algebraic simplification and are used to reduce complex mathematical expressions. Let's start with the commutative law. This law is all about flexibility. It states that the order in which we add or multiply numbers doesn't change the result. For example, if we have two variables, a and b, we can add them in any order. A plus b is the same as b plus a. Similarly, for multiplication, a times b equals b times a. The order of operations doesn't affect the result. Now let's move on to the associative law. This law is about grouping. It tells us that the way we group numbers in an addition or multiplication operation doesn't change the result. Let's take three variables this time, a, b, and c. According to the associative law, a plus b plus c equals a plus b plus c, regardless of how we group them. The same holds for multiplication. A times b times c equals a times b times c, no matter how we group them. These laws may seem simple, but they are incredibly powerful. They allow us to manipulate mathematical expressions, to simplify them, and to solve them more easily. Let's look at some examples to demonstrate these laws. Suppose we have the numbers 2, 3, and 4. According to the commutative law, we can add them in any order, and the result will be the same. 2 plus 3 plus 4 equals 9, and so does 4 plus 2 plus 3. Now let's multiply them. 2 times 3 times 4 equals 24, and so does 4 times 2 times 3. The order of operations doesn't change the result. Now, let's apply the associative law to the same numbers. If we group 2 and 3 together, and then add 4, we get 9. If we group 3 and 4 together, and then add 2, we still get 9. The same holds true for multiplication. If we group 2 and 3 together and then multiply by 4, we get 24. If we group 3 and 4 together and then multiply by 2, we still get 24. The way we group the numbers doesn't change the result. These laws show us how we can rearrange our expressions without changing their value. Now, let's explore the distributive law and the absorption law. The distributive law is one of the essential properties in algebraic simplification. It states that multiplication distributes over addition. In simpler terms, when you multiply a number by a group of numbers added together, it's the same as doing each multiplication separately. In the world of Boolean algebra, this would look like A and B or C equating to A and B or A and C. Imagine you have a group of friends represented by A, and you're deciding whether to go to the beach, B, or the cinema, C. According to the distributive law, the whole group's preference for the beach or cinema is the same as each individual friend's preference for the beach or cinema. Now let's look at the absorption law. This law is like the ultimate simplifier. It states that A or A and B equals A, and similarly A and A or B equals A. This law is like saying if you have an apple, represented by A, and you have an apple and a banana, represented by B, you still just have an apple. The banana doesn't change the fact that you have an apple. To illustrate, let's say A represents you watching your favorite TV show, and B represents you eating popcorn. According to the absorption law, whether you're just watching your favorite show or watching your show and eating popcorn, you're still watching your show. The popcorn is a delightful addition, but it doesn't change the fact that you're engaged in your favorite show. In the realm of algebraic simplification, these laws play a crucial role in reducing complex expressions into simpler ones. They help us break down complicated equations and make them easier to understand and solve. It's like having a magic key that unlocks the simplicity in complexity. These laws help us simplify complex expressions into simpler ones. Let's move on to De Morgan's laws and the principle of double negation. De Morgan's laws are a pair of transformation rules that are both valid in the Boolean algebra system. These laws are named after Augustus De Morgan, who introduced them. They give us the ability to express conjunctions and disjunctions in different forms. The first of De Morgan's laws states that the negation of a conjunction is the disjunction of the negations. In simpler terms, the opposite of this and that is not this or not that. The second law is the mirror image of the first. It states that the negation of a disjunction is the conjunction of the negations. In other words, the opposite of this or that is not this and not that. These laws are incredibly useful when simplifying complex Boolean expressions, particularly those involving negations. Now let's turn our attention to the principle of double negation. This principle is quite straightforward. It simply states that the negation of a negation is the original proposition. In other words, not something is just something. This principle often comes in handy when we are simplifying expressions, as it allows us to remove pairs of negations, making the expression easier to understand and work with. Let's illustrate these laws with some examples. Say we have an expression not A and B. According to De Morgan's first law, this can be simplified to not A or not B. Or if we have not A or B, this can be simplified to not A and not B, according to the second law. For the principle of double negation, if we have not A, this simplifies to A as per the law. In conclusion, De Morgan's laws and the principle of double negation are powerful tools in the algebraic simplification process. By applying these laws, we can transform and simplify complex Boolean expressions, making them easier to understand and analyze. These laws can help us simplify expressions even further. Lastly, we have the consensus theorem. This theorem is a useful tool in Boolean algebra, helping us simplify complex expressions. The theorem states that for any three variables a, b, and c, the expression a and b, or a prime and c, or b and c, simplifies to a and b or a prime and c. To put it simply, if the first two terms of the expression share a variable, and the third term is the combination of the remaining variables, the third term can be dropped. To see this theorem in action, let's simplify a complex algebraic expression using all the techniques we've discussed. Consider the expression a and b or c, or b and a or c. First, we apply the distributive law. This gives us a and b, or a and c, or b and a, or b and c. Next, we use the commutative law to rearrange the terms, resulting in a and b, or b and a, or a and c, or b and c. Notice that a and b and a are the same, thanks to the idempotent law. So we can simplify this to a and b, or a and c, or b and c. Now we can apply the consensus theorem. The first two terms share the variable a, and the third term is the combination of the remaining variables b and c. According to the theorem, we can drop the third term, resulting in a and b or a and c. Finally, we apply the absorption law. The expression a and b or a simplifies to a, leaving us with a or a and c. Applying the absorption law again, we get the simplified expression a or c. Through this example, we can see how these techniques come together to simplify complex expressions. By mastering these techniques, we can simplify any Boolean expression, helping us optimize digital circuits and improve their efficiency. To wrap up, let's summarize what we've discussed. We started with the basics of algebraic simplification, moving on to explore Boolean identities, which are the cornerstone of this topic. From there, we delved into the commutative and associative laws. which ensure the consistency of results irrespective of the order or grouping of terms. Next, we discovered the distributive and absorption laws, allowing us to break down complex expressions into simpler, more manageable components. We then studied De Morgan's laws and the concept of double negation, which are vital for manipulating and simplifying Boolean expressions. Lastly, we looked at the consensus theorem and walked through an example simplification, providing a practical illustration of these principles in action. These techniques are all invaluable tools in your algebraic toolkit, aiding you in reducing complexity and solving problems more efficiently. Remember, algebraic simplification is not just about simplifying expressions, but also about sharpening your logical reasoning skills. Keep practicing, and you'll get the hang of it in no time.